Well, welcome back, and as ever, I do hope you and your family are keeping well. So what we're going to look at in this lesson is how to plot graphs correctly, and also how to calculate the gradient of any line that you get on your graph. So this should be useful if you're doing GCSE, but we're going to take it a little bit further and perhaps talk about A-level as well. So those of you that I teach know that I bang on and on and on about graphs, and with respect, there are times when I'm a little bit shocked that graph drawing skills aren't quite as good as they should be. I also don't fully understand why, because it's basically a simple set of rules or instructions you have to follow. Okay, now we draw graphs for a very specific reason. We want to show how data changes, and sometimes the gradient of the graph, or even the area under the line, has some meaning in physics. So what I thought we'd do is imagine an experiment where we want to find the average velocity of something. So find the average velocity. Okay, now you know that to work out velocities, okay, it's distance divided by time, or more correctly, displacement divided by time. So you need some measure of time, and you need some measure of the distance or displacement you went. So let's have our data table. Okay, and this is another area where things seem to go wrong. Data tables, really simple. Yeah, okay, use a ruler. So I've got one here, and put your headings on. So here they go. And I'm going to choose to do the columns this way around. The time measured in seconds. Yep. And I'll use D for distance. I know it should be S for displacement, but it'll get confused otherwise. Okay, so we'll keep it simple. Right, now, you've probably already switched off because you said, oh, this is far too simple. Bear with me, okay? Let's say our starting time was 0 and we hadn't moved anywhere. We took some readings. You'll be pleased to see that I'm not going to write them all down. Okay, and then the maximum value of time was 18 seconds, and the maximum value of distance was 105 meters. So we've got our table, we've got our data, okay, we've got no decimal places here, so that's all fine, okay, and we've put the units at the top, not in the table. Okay, so how do we draw the graph? Well, what I always say to students is, look at the size of these numbers and make them a bit bigger to an easy number that's a bit bigger. So that's near to 20, that's near to 110. Okay, so I'm not going to worry about these numbers first. I'm just going to draw my axes. Okay, so I'll draw my axes over here. And I have to remember what I put on the crossways x-axis and what I put on the standing up y-axis. Okay, so this is going to be time measured in seconds. So I've got what I've measured and what units I've measured it in. And here it's going to be the distance or displacement in meters. So D in meters. All good. Okay, so don't forget to put your units on. Now, remember what I said about making this a bit bigger. Okay, the next biggest number that's an easy number. Okay, so I'm going to make that 1820. So I want to fit up to here numbers that go up to 20. Across here. Apologies, the time to 20. Okay, so I'm going to start at 0. Okay, and please, please, please make your axes linear. Okay, I always tell the story of when I first came to teach at a school, and I asked the kids to draw a graph, and they got the numbers like 1, 3, 5, 18, and they went 1, 3, 5, 18, and it's like, we've got some work to do here. Okay, because they spaced out 1, 3, 5, and 18 evenly. No, this is like a ruler of time. Okay, so 18, nearly 20. So make your scale something like 2, 4, 6, 8, 10, 12, blah, 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 and make it up to that slightly larger and easier number. Okay, distance, 105 you could do that one, granted. I'm going to make it 110. So I'm going to go 10, 20, 30, 40, 50, 60, blah, 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 right the way up to the top. And I'll end up here at maybe 110. Okay. Now, there are times that you'd make those numbers bigger, but I'm not going to worry about that at the moment. Okay. But that's the way to get your scale on. Okay. And obviously, you put all the numbers on here, but don't put the units after them. The units are dealt with there. Okay. So the next thing we're going to do is we're going to plot our data and draw the line or curve of best fit. So let's quickly recap on what we've talked about so far. The first thing I said was use a good scale on your graph. Okay, so go up sort of evenly to a number that's slightly bigger than the ones that you've got. Okay, we talked about labeling the axis. Okay, bit of a problem there. I never quite know what the plural of axes is. Anyway, label them with the correct measurement and the unit. Okay, and then we're going to plot our points. So small. Some people use pluses. Some people use crosses. There is a good reason for using either, to be honest with you. Okay, for the points, and we'll do that in a second. And then finally, you want the line or curve of best fit. Now, for A-level students, I hope it's clear why we use a best fit line. GCSE, people struggle a little bit with that. Okay, so I'll explain why we use a best fit line. So we're going to plot our data points. So I'll go for little pluses, this sort of thing. Okay, I guess that one wouldn't be there really, would it? Because we haven't got numbers that high, but that doesn't matter. Now, the crucial thing is when we do experiments, we get a little bit of variation. We get a little bit of experimental error. Okay, human error in the timing and errors with measurement of the distance in this case. So the thing to point out to GCSE students particularly is these numbers aren't exactly right. Okay, yes, they're what we measured, but they kind of have a bit of wiggle on them because you weren't exactly right with the distance, you weren't exactly right with the time. Okay, and we'll look at error bars later on for A-level students. So, okay, I've spent years trying to teach out how you do the line of best fit, okay, and I've come up with this solution. Yeah, there are some exceptions to this, but this solution, that generally it's what you can draw with a ruler. It's that simple. Okay, so for example, it's either a straight line or it's how you can curve a ruler. Yeah, it's that simple. Okay, so you never join the points. Yeah, you use a ruler. I look at that and I go, ooh, yeah, that one almost looks anomalous, in fact. Difficult to say, but maybe we'll keep it in. We'll draw our line of best fit. So shall I choose red? I don't know if this pen works. Okay, and I'm going to get a ruler. It helps if the ruler is a little bit see-through. I'm going to average the points, assuming there are no anomalies. And there we go. Okay, I tried my best. I'm not suggesting that's a brilliant line of best fit, but it's the best I could do today. Okay, so that clearly is what you draw with a ruler, and it's that. It's not this, and it's not that today. At A-level, yes, of course, we have sine waves and things like that, but don't worry too much about that. You tend not to plot them directly. Okay, so I'll say it once more, what you can draw with a ruler or bending a ruler. Never join the points. Okay, if you join the points, two things are happening. Firstly, you're saying that these are measured absolutely accurately. Okay, so they're kind of bang on points. And secondly, and this is a bit I find difficult to explain, you're suggesting that things in science on the big scale change in a sort of jerky way, and they don't. When you speed up or slow down, your speed varies sort of smoothly. In this case, yeah, distance divided by time is meters per second. So the gradient of this graph will be the average velocity. So let's look directly now at how we can find the gradient of a straight line graph. So we've got our graph here. Obviously, we'd have some numbers on the axes. And I'm suggesting, though you don't need to follow this bit through, that we're trying to work out a speed by measuring a distance divided by a time. Okay, so distance divided by time is actually the gradient of this graph. So let's look at what we mean by the gradient. Okay, well, in this case, the gradient, is how much we go up compared with how much we go across. So on this graph, it would be the d value divided by the t value. Yeah, how much up compared with how much we go across. Now, what we really mean, and this is a little bit A-level-y, is how much has our distance changed from where we started, okay, and how much further on has the stopwatch gone from when we started. So, what we're saying is the change in, this is delta, big delta. Big delta is a lazy way of writing change in. It's the change in distance divided by the change in time. And we know that that would be our speed. Okay, I'll use v, velocity or speed in this case to keep it simple. Now, I'm not trying to teach you how to calculate speed, but what I'm saying is that gradients have a use at GCSE and at A-level. So how do we get the gradient of a straight line graph? Okay, well, the rules are pretty simple. Okay, you need to measure how much you go up by compared to how much you've gone across. Okay, and the way to do that is to draw the biggest triangle you can. Okay, so what I mean by that is, let's start. This one happens to start at 0, 0, so it's a bit of a special case. Let's start here, go along the axes, and then go up to the line. Okay, and that's drawing a large triangle. So here we go. Let's go along here. Got a slightly better green pen. End of term pens. Yeah, so running out. So let's go across here, and then let's go up to the line. Okay, so I've drawn, that should be absolutely on the x-axis, but I'm making a point here just so you can see it. Okay, now I've drawn the biggest triangle I can that touches the line. There's a little trick here. If you're starting at 0, 0, why don't you pick a point here that's a really nice number, okay, on the line? Maybe that might be a number like 100, which would make it really easy to work out what that point is, okay? And then, once you've got your big triangle, it will give a gradient if you use a little one, okay? It'll be exactly the same steepness, but you get more error in your answer, okay? So then what you do, is you divide the change in how much you've gone up by. So I'll rewrite this as, the gradient is equal to the change in the y value divided by the change in the x value. Okay, some teachers call this rise over run. So here we go. We've gone from this point to that point. Okay, so what change in y value is that? And we've gone from this point to that point. What change in x value is that? Okay, now listen really, really carefully to this bit, because this is where students get it wrong. Okay, it is not this number divided by that number unless you started at 0, 0. Okay, so I'm going to write here, really importantly, watch for 0, 0. Okay, hope you understand what I mean by that, because if you drew the triangle here, which would be totally okay, okay, you might start at 3 and end here at 10, so this would be a change of 7. Yeah, not 10. And it's an absolutely classic mistake that students make. Okay, I'll make the point here as well. If this one starts at 1 and ends at 100, that has changed by 99, not 100. But if you try, like I've tried to show this going through 0, 0, then it's easy. Okay, it's much easier. But do look out for when you draw the triangle not starting at 0, 0, because not all graphs do. It might cross the axis a bit higher up. There might be a plus C in the maths, as it were. Okay, so you've now got a good understanding of how you find the gradient of a straight line, and it all hinges around two things. Draw the biggest triangle you can, okay, and then work out what numbers you went from and to, and that's the change in y, and you went from here to there, that's the change in x, and divide them, and if you do that, you've got the gradient of your straight line. So now let's get into the realms of slightly more complicated graphs, graphs that have a curved shape. And what we're going to do is work out the gradient at a particular point on the graph. Now, this is very much at A level, because at A level, when we do oscillations, we might be looking at graphs that have this shape, and we might be asking questions about how the gradient changes. The gradient will, of course, be meaningful, especially if this was a displacement time graph, then the gradient at any point will give us the velocity. But you can come back and do that lesson at another stage. So I'm going to pick a slightly tricky example. People don't usually make the examples this tricky when teaching. But I think if you understand this one, you'll understand every one. Okay, so we could, you can imagine it's a part of that sine wave, but I'm going to make it a little bit different. Let's have a curve like that. Okay, I'm not suggesting this is anything particularly in physics. I'm just saying there's a curve. And what would happen if we were interested in the gradient at this point here? Okay, now you'll see that it begins steep positively. That's really important. You spot it's a positive gradient, and gets less steep and less steep and less steep. Look at that line where my pen is. It's called the tangent. And less steep and less steep, and then it levels out. And then maybe later on, it's unlikely, but maybe the graph will have a negative gradient that's changing. Okay? Well, the rules for doing these are pretty much identical to what we've done already. Okay? It's a case of draw the largest triangle you can. Okay, but this is at the point. Okay, at the point you're interested in, because the gradient is changing. Okay, and to do that, yep, you need to understand how to draw a tangent. Okay, I'm not talking about sine cos tan on the calculator at the moment. I'm just saying the idea or the concept of a tangent. Okay, I hope I can get this right. I've got one shot at it. Yeah, we want to draw how steep the graph is. No. Yep, how steep the graph is at that point. I'm not sure if it comes over on the video, but it's actually the shadow of my ruler. So I'm going to try. I'm going to try and get that right. It always helps to have a see-through ruler, guys, so you can get this right. So there we go. So I've drawn a tangent at that point. What makes it a tangent, in simple terms, is the kind of bit there and the bit there is the same. Okay, it represents the gradient at that point. And do you remember what I said? It's the biggest triangle. So what you're going to do is make your triangle. There it is. Okay, and I'll just say it again, the biggest you can. Okay, don't do little tiny triangles that will have lots of error in them. And then you can see that this length here is the change in the x value, and this length here is the change in the y value at that point. Okay, so the gradient at that single point will be the change in y over the change in x. And if you're doing A level, you can't get away from that, because we're going to be looking at sine and cos waves and things where there are constantly changing gradients, and the gradients will tell us things like the velocity of the thing that's moving, or even the acceleration of the thing that's moving. Okay, so now let's look at how we use gradients. So an earlier example, we looked at how we use the gradient of a straight distance time graph to work out the speed or velocity. A little bit GCSE-ish that. But at A level, it will get a little bit more complicated. And I talked to you about sine and cos graphs and why points on those are really important. But what I thought I'd do now is look at an equation where we can get some values from the equation from drawing graphs. And this is something you'll be expected to do in detail at A level. Okay, so I hope you're all familiar with an equation of motion, and this is the one for constant acceleration. So v equals u plus at. What speed we do now, is the speed we were doing, or the velocity we were doing, with an added bit on top. And the added bit is what our acceleration was and how long we did that acceleration for. Okay, just as an aside, meters per second multiplied by seconds becomes meters per second. So that's this speed or velocity that's added on. Okay, now if you look at what that equation means graphically, okay, if I quickly draw a graph, I hope you're happy that the gradient of a velocity time graph is the acceleration, but if not, watch this. Okay, so there's the velocity, which is our y value, and here's the time, which is our x value. Okay, and we were trundling along, and then we speeded up. So we were trundling along, and then we speeded up with a constant acceleration. Okay, so let's look at this in a little bit more detail. Now, one or two of you will straight away say, yeah, got it. The gradient of the line, because we learned it at GCSE, probably, is the acceleration. But let me show you another way of looking at this. Okay, this equation can clearly be written v equals u plus at, but it can also be written v equals at plus u. Okay, and you'll see that that sort of helps us get the equation of our line. Because if you remember, this is sort of y equals mx plus c. Okay, so looking at that, oh, I get it. Okay, our y value, that axis. Okay, m is the gradient, so the acceleration will be the gradient. Time, yep, that's the x-axis, and the plus c is the intersect. So this point here, I use the red pen, this is our c value, yeah, and we notice from this equation that this here, the gradient, will give us the acceleration. So we're up and running, yep. You use a ruler for this, but bear with me because I'm doing this quite quickly. So here we go, biggest triangle that fits nicely. Okay, so there's my my triangle, and obviously that should be horizontal. So here we've got a change in y value and a change in x value. So the change in y, how much we go up by, divided by the change in x, will give us our acceleration. Okay, so it's a clever way of using graphs, looking at formula and realizing, oh, in this case, to work out the acceleration, we need the gradient. So there we go, draw the biggest triangle and work out the gradient. But do you remember the catch? Do you remember I said earlier on, be careful for 0, 0. Okay, this change in x is fine. It's starting at 0 and going up to a value. So this might be 10. Okay. But this is not starting at 0. So this might be 90 going up to 110. So that number is 90 to 110 is plus 20. So be really careful with that you don't just divide this number by that number. Okay, it's only that bit of the rise. So there we go. That's using a gradient to get a value that we needed in an equation. So now let's look at our last example, and it's time for the curves. So what happens with non-straight line graphs? Okay, and what I'm not going to do here is just get the gradient of a graph that's curved. We know how to do that, but I'm going to show you how we can get information in an equation from a graph and how we can straighten out that graph. So this is really a little bit more of an A-level concept. Okay, so another equation of motion there, S equals ut plus a half at squared. So yeah, get your head around this one. Constant acceleration formula. So how far have you gone? Well, it's what speed you were doing multiplied by how long you did it for, yeah, added to the bit where you accelerated. Okay, the half at squared graphs quite nicely as well, but we won't deal with that today to show you where that comes from, because that must be measured in meters. It must be a displacement. Okay, so here we go. You'll notice here that the displacement that you do, okay, is proportional to t squared. Yeah, S has a connection here with t squared, plus the sort of bit that you've done in advance, as it were. So if we plot a graph of your distance away from where you started as time ticks away, this graph will not be straight. So there's your displacement, and there's the time, and the graph will curve upwards. Okay, so perhaps we'd want to get out what the acceleration is here. Okay, well, it's tricky to find the acceleration here because gradient here is not acceleration. Okay, meters divided by seconds is not an acceleration. So could we straighten out this graph? Well, if S is proportional to t squared, then the obvious trick is to plot that relationship. So plot S, yeah, against t squared. So I won't go into numbers and all the detail of this, but what you must do, of course, is on your table of data is add another column that has t squared in it. Okay, so that will give you a linear graph. So if you plot your graph, here we go. There it is, and we'll make that S, and we'll make that t squared. Okay, we'll get a straight line. Now I'm going to forget about the ut for now, because that's not the bit that's accelerating, and I'm interested in the acceleration. So we'll just set it to 0. I love the way math teachers can just go, well, just set it to 0 or what have you. Okay, so we'll have a graph like this. I don't need to say this to you at A level, but please get out of the habit my junior students think that every graph that's straight line has to be at 45 degrees. Yeah, no, okay, it's just the graph that it is. Okay, now notice our equation. I'll do it in purple. S equals ut plus a half at squared. Let's just swap it round a bit. S equals a half a t squared, yeah, plus ut. Okay, and let's compare that to the equation for a straight line. Okay, so y equals mx plus c. So there's our y, yeah, our s value. There's our x value. Okay, our plus c, I've just said is 0 for the moment. Okay, so we didn't have an initial velocity. Okay, we didn't have a u. And look, there is our gradient. So we do the usual thing. We draw the biggest triangle we possibly can. You would clearly start at 0, 0 here. Just for the sake of the teaching, I'm going to start a little bit higher up. Okay, so there's my triangle, and that's how much we've changed our displacement by. So that's the change in y value. This is how much the t-squared has changed by, the change in x value. Okay, and the gradient here will be the change in y over the change in x value. Okay, remember again, of course, on my example here, it's not this number, okay, this number divided by that number, because I haven't started my triangle at 0, 0, so I've got to take away from here to there. I've got to find the length of that line, I suppose you could say, t-squared, and that line, okay, an easy mistake to make. And then you'll notice that that all equals the gradient, yeah, which is a half a. So clearly here, yep, the gradient gives us half the acceleration, so the gradient times 2 will be the acceleration. Just separate that up there, okay, so it doesn't get confused with all this maths I've done here. So you can see how a number of things we've done here. We've taken our equation, we've plotted it to show that it isn't a straight line, okay. We've found the proportionality, okay, and therefore plotted that one against that one to give a straight line, okay. We've looked at the formula and found that the formula of this line gives us a half a for the gradient, so we work out the gradient with our big triangle, and we've got half the acceleration, and then we double the gradient to give us the actual acceleration that we got in our experiment. So a quick whiz there through graphs, gradients, and why gradients are important in physics, and how to calculate them, and then how we use the gradients of graphs to give us values that we need in equations. Anyway, I hope you found that useful and I didn't rush it too much. I'm sure I'll be doing another physics lesson before long. As ever, enjoy your physics, and I look forward to seeing you again next time.